This paper is jointly produced with a former graduate student of mine, Rami Morin-Chassé, and it in fact came out of his dissertation, which is to say that anything that's right is Remi's responsibility. It's his production. Anything that's wrong is mine. Shameless promotion. I promised the publisher of Now Publications, Strategic Behavior in the Environment is published by Now Publications. Everywhere I go, I throw this little plug out. Send us papers, please. So let me start off here by talking about some patterns that one can pick up in the data with respect to resource use and different kinds of ingredients into energy production broadly writ within the United States. This is all U.S. stuff, by the way. So the panel on your left displays two time series. The higher up one is as production of, or the amount of coal that's going into electricity production in the United States. The one below that, because I'm from Wyoming, is from the major production basin in Wyoming. It's called the Powder River Basin, the acronym to which is PRB. And you see in this, in both of these time series, you see this particular pattern that somewhere around 2007, give or take, and this sort of touches on some of the things that Frank told us about. Somewhere around 2007, the use of coal crested in the United States, and it's been pretty much monotonically declining ever since. There's a little hiccup. Frank picked up on the role of the Great Recession. What he didn't say was that as we came out of the Great Recession, and you can sort of see this in the little tiny uptake in 2009, 2010, use of coal went up for a little tiny bit, but if you sort of smooth out the trough that comes about because of the recession, you can just see that the use of coal is falling off a cliff. On the right is a time series of, over more or less the same period of time series of representing monthly use of renewable energy, again within electricity markets. The one on the left for coal, that's annual, so it doesn't have nearly as much variation as the one on the right. There's a couple patterns that come out of this. One obvious feature is that renewable use is rising quite consistently over time. The other, which is other people have spoken to this, and Catalina, I think, will talk about this as well, is that there's substantial variation across time, within a narrow band of time. This is month to month, she'll talk about day to day, but there's this variation, intermittency in the use of renewables and electricity. And so the thing I'm going to pick up that Frank made me think about in his presentation is that in order to really facilitate the use of renewables, and this is off script, this is not part of my presentation as I originally conceived it, but in order to facilitate the use of electricity, of renewables in generating electricity, you have to have something that stands behind and is able to offset these great variations. And realistically, coal isn't it. Right? It's very difficult to ramp production from coal power plants up and down. It's really trivial to ramp power production from natural gas power plants up and down. So one thing that I suspect is true, and I would challenge Frank and his ex-teammates at EDF to think about this, is that the fracking revolution didn't just unleash natural gas production, it unleashed a set of circumstances that facilitated the rise of renewables in a way that coal power production could never have done. So thinking about this as sort of on a broader scale of time over the course of decades, again thinking about the role of these two ingredients, coal and renewables, in generating electricity, here's a time series that shows you the fraction of electricity in the United States that's attributable to each of these two sources of energy inputs. And again, you see, we can have a light. Yes, excellent. So from about 2007 forward, coal's share of electricity production has really collapsed. I didn't write on these, I should have done, I'm sorry. All of this data is taken from the U.S. Energy Information Administration website, so you can go and produce these graphs all by yourself if you should so desire. You see as well that there's been this sort of steady increase from, at least from 2000 forward, in the role of renewables. Now, the the point that I want to take away from these graphs, there's a couple things that I want to draw from these diagrams. One important thing is that there's been this steady, persistent, simultaneous use of both types of energy inputs, renewables and non-renewables, or fossil-based fuel, as in coal, and non-fossil-based fuel. And indeed, over the course of the last, say 10 years or so, there's been this evolution under which there seems to be something of a substitution away from one into the other, perhaps for more complicated reasons, as I suggested a moment ago, but nevertheless. So is this just a passing trend? Is this something that we should expect to persist going forward? So the next two pictures that I'm going to show you, I'm drawing from a presentation that a colleague of mine gave quite recently. He's an expert on coal production in the state of Wyoming. And this first diagram here shows you the planned retirements of electric power producing plants in the United States that are presently using coal. So over the course of the next 8 years or so, we expect about 150 coal-fired power plants to be retired. About half of those come from the state, which is why it matters to folks in Wyoming. And this is a substantial share of the amount of coal that's being produced in the state. Again, why it matters to the state in Wyoming. So is this just also a passing fad? Well, no. The thing on the right here gives you an idea of the kinds of plants that are the names of the plants that are about to be retired. And you can see that this is a pattern that is not just over the course of the next few years. So the graph on the left goes through 2025. This goes well beyond. Right? This is a phenomenon, this emerging trend where coal-fired power plants are going to be retired, and thereby we will reduce the use of coal and presumably substituting for it things like renewables. This is not a passing fancy. This is going forward. This is going to be an important phenomenon. So here's a clip that I drew off the internet. This is from a story that was recently published in Reuters. The website for this is as indicated here, and I picked out two choice quotes. One of these is sort of touching on a theme that Frank hit on, that there'll be this increasing capacity, not just in wind, but solar as well, that we expect the capacity of solar plants to double. So this will be a substantial increase over the course of the next, 10 years or less. And at the same time, there's going to be this major disruption associated with renewable energy use, not just for oil, but also for natural gas as well. Okay, so this idea that you're going to see renewables supplanting coal is a kind of a bellwether, but it's not the only thing that's going to happen. And so there sort of seems to be this trend going forward, the rise of renewables. So there's a tie into this. I'm just going to say this in passing. There's a connection between the story here and notions of something like global well-being, which you might summarize very loosely underneath the umbrella of sustainability. And the gist of this is that if you're going to have a path going forward where some measure of well-being is monotonically, or at least weekly monotonically increasing, so we don't have people getting worse off over time, which is a sort of a standard notion of sustainability, then something has to happen to supplant the so-called dirty energy. And presumably that's going to be investment into things like capital that is able to support clean energy. So this transition that we're thinking about here, away from conventional fossil fuel-based dirty energy into something like renewable energy, which we might think of as being cleaner, scholars have been thinking about this for a while. And in my mind, there's a certain parallel here to the intellectual pursuit of the environmental Kuznets curve, where you have patterns whereby rising income leads to a non-monotonic relationship with pollution levels in some particular source. Maybe it's in carbon dioxide, maybe it's in some other pollutant. And in order to model this particular phenomenon, scholars came up with a variety of models, some of which were quite strained. stylized, hackneyed, unrealistic. They didn't really capture the full gist of what was going on. And in the same way, and this is not meant to be a criticism, you start with baby steps and then you work your way forward. So early papers that thought about this transition from non-renewables into renewables, where there might be patterns that didn't seem to exhibit monotonicity. We hit a point and we switch forever. Some of them have a phenomenon where you have double switching. You start off with renewables. Think of back in the day when we used firewood for our source of energy. And then we switched to coal. And then maybe we're going to switch back to renewables. That doesn't really capture the flavor of this. A more recent paper by Kees Vithagen and Rick Vanderplug does a better job of this, because there's a period of, not just a moment, but an interval where you have simultaneous use of both types of energy fuels. And this is more satisfactory. They get this particular result, however, because investment in what you might think of as traditional productive capital overshoots its steady state level, and so then it has to decline over time. We allow it to decay without investment into it. And it's during this decline phase that you can have simultaneous use. So if you believe this is a story that explains things, then you have to believe that we've built up too much capital. And maybe you do, and maybe you don't. But what both of these lines of analysis miss is the role of capacity in the production of renewable energy. Partly because the conventional model, going back 10, 15, 20 years, the conventional model looked at renewable energy as being something like a backstop technology. The conventional model of a backstop technology, dropped on top of a hoteling model, is one in which there's a high, relatively constant, possibly perfectly elastic supply curve associated with the backstop, here, renewable energy. But that's not really what's going on. Renewable energy doesn't have high marginal cost. It has low marginal cost. It has high setup costs. And it doesn't just have high setup costs and low marginal costs. The production of energy from renewable sources is constrained by the capacity that's in place. And most of these analyses, in fact, I can't think of one aside from the paper I'm about to talk about, which has got Remy's name on it and my name on it. I can't think of one that seriously confronts this issue of capacity. So this is kind of what I'm going to talk about here, is a model in which there's investment into renewable capacity from which renewable energy is produced. It's not a kind of a conventional benefits and cost model. It's couched in the context of a growth model. So in a neoclassical sense, there's a kind of a neoclassical production function, and then there's this aggregate utility function, and output can be divided between different kinds of things. So the cost associated with investment in capital, renewable energy capital, is the opportunity cost of not using that output to feed into consumption. So here's the story that we're going to suggest, that there's relatively low, possibly zero, possibly not zero marginal cost. You can think of a story in which the places that you would cite this capacity, the land, maybe in the north, maybe closer to the south, maybe where there's open space, maybe where you have to tear down trees. It's heterogeneous. So there's a certain Ricardian flavor to this. And as you expand capacity, it comes at ever higher cost. There's also the possibility that there's learning by doing. And this is an important phenomenon in the context of renewable energy. So over time, as we build up the capacity to produce renewable energy, we learn how to do this better, and the opportunity costs fall. So both of these phenomena in opposite directions suggest that there's a stock effect, that the cost associated, or the opportunity cost associated with investing in renewable energy depends upon the stock at hand. It's also true that there's depreciation associated with use, and you can think here of windmills as they turn, they wear out. Similarly, if you have solar panels, there's chemical reactions associated and they decay over time. So these are both features that would suggest that the ability to produce renewable energy depends on the stock, but it also depends upon the flow of usage, and the flow of usage decays in a manner that is, I'm going to suggest, is at least broadly similar. Is that me? I thought I had 25 minutes. No. What slide am I on? I didn't count. Okay. Well, all right. So anyway, there's going to be this effect that more capacity makes it easier to produce, more consumption makes it more costly. Since Simone's told me to shut up soon, I'm just going to say that the nature of this, where this sort of shows up, there's two stocks in this story. There's a conventional energy stock. You can think of this as the stock of coal, which follows a conventional hoteling dynamic. The time rate of change in that stock is inversely related to the rate of usage. The renewable stock, which I'm denoting by X, depends upon the rate of change in that depends on the standing stock. So this can either capture the Ricardian effect or the learning by doing, and maybe be working at the same time but in opposite directions, as well as the amount of energy, E for energy that's being used. H is for harvest. So as I use more, harvesting renewable energy, if you like, it makes it harder and harder to add. So there's a certain parallel to this. Part of the notation here is purposeful in this way. There's a certain parallel here to fisheries models. I haven't the time to walk through this, just to say that this is the kind of the nature of the problem. I'm interested in maximizing intertemporal objective functions, the discounted flow of utility, where utility depends positively on consumption, possibly depends upon the state variable associated with renewables, and P for pollution stock. So I dislike having pollution, and pollution here is sort of global carbon stock. You get an addition to the global carbon stock depending upon the rate of use of the non-renewable, and then maybe there's going to be some expenditure on abatement. And the expenditure on abatement is taken from energy usage, and so it's costly in the sense that you can't use that energy for other things, like producing widgets. So let me sort of cut to the chase in this. This is a complicated model. So actually, let me not cut to the chase quite yet. This is a complicated model. I have three state variables, 4 state variables. Oh my God. That means I've got 8 variables because I've got to have a co-state variable with each of these things. I got 2 control variables. Wait, no, I have 3 control variables. Maybe I have 4. You can't solve this. You can't solve this analytically, right? You have to solve this numerically. And so the stuff that I'm going to go through here towards the end are the result of simulation analyses. The first of these sort of, I'm going to call this the baseline analysis, displays a pattern where consumption rises across time, capital of renewables rise across time, and the renewable resource that's used goes up over time. So this broadly captures, the bottom of these, figure 9, captures the essence of those first graphs that I showed you. The top left one, figure 7, supports the idea that this is a sustainable path. At the same time, you can get a sense for what's happening for energy share. So here's Q for non-renewable, H for renewable, and you can see the renewable energy use in this baseline model rises monotonically across time. At the same time, the non-renewable use falls, and at a moment, right here, you cease using the non-renewable and you switch completely to renewables. And I think I'll just leave it at that. So in this particular setting, finding a path that generates sustainability is a little bit delicate. You have to have just sort of the right amount of the initial capital stocks of each of these things. But it turns out that if you don't have too much of either, if you don't have too little of either, then sustainability is in the offering. Actually, let me leave this one thing up here. There's this one path, there's one path that I'm calling path 5 that has this weird feature that it initially, for most of the path you have utility rising, but there's this momentary drop. And this particular path I want to talk about some at length as sort of a policy experiment. So we're going to interpret this as a moratorium on renewables. And true confessions here, when Remy dreamed this up, this was maybe 4 or 5 years ago, we just thought it was sort of an interesting story. We didn't actually think anybody would seriously entertain this. And then along came 2016, and now this actually is US policy. So this really does seem to be in place, that there's at least a subtle, if not an overt, attempt to push down the use of renewables in order to promote non-renewables. And you can think of this as being a little bit like having a moratorium or a freeze on the amount of investment in renewables. And what this And that's this path right here. What you get out of this is that there's sort of this momentary loss in utility, which stands to reason because we've deflected attention away from what would have been sort of the laissez-faire approach. We invest a little bit less in renewables, and that has to come at a cost, and that is a utility cost. Now, the other side of the coin might be that we think about some sort of a policy that promotes renewables. You could think of this as a renewable portfolio standard, something that dictates the ratio of energy that comes out of renewables. And I'm illustrating here, so this on the left is the amount of this renewable energy that's being produced. The blue line that I'm showing you there is the very same as the blue line in this top central figure here. Now imagine that in that setting, we dictated the initial amount of renewable energy. And in this particular experiment, we just arbitrarily doubled it. Okay. The units are not so important. It's the relation between these, so from point 1 to point 2. And what you see out of this is that at the same time that we push up the renewable use, that raises costs, as it were, associated with production. And so there's a little bit less production that comes out of this. There's a little bit less usage of non-renewable energy that's imported into this. And accordingly, the time path of renewable energy or non-renewable energy, it drops as well from the blue line to the dashed line. And you'll note here that it strikes the x-axis at an earlier point in time, and that's the moment at which we cease using non-renewable energy. So this renewable portfolio standard, among other things, pushes forward in time the moment at which we switch completely from non-renewables to renewables. Now, you might ask yourself how this translates into the fraction of energy that comes out of renewables. So these are levels, right? And if you look closely, you'll see that the intercept here is 0.5 and the intercept here is 0.1. They add up to 0.6 in these arbitrary units. Here 0.4, here 0.2, so they add up to about the same. And so it would seem that the fraction of energy associated with renewables has gone up. And it's not just that at the moment, it shifts up entirely. Now, I'm imagining that somewhere along the line, there's somebody who's going to ask me about the green paradox, so I'm over time, but I'm just going to do this, and then I'll quit. How's that? So what I did just while I was sitting here this morning was to calculate the percentage change in each of these types of fuels. And just the graph to your left is the percentage change period on period of the use of renewables. And one thing that you see is that by invoking this renewable portfolio standard, the level goes up, but the rate of increase goes down. On the right is the rate of change in non-renewables, and you see that the invocation of this renewable portfolio standard accelerates the rate of depreciation in the use of non-renewables. And so there's a certain parallel here, there's a certain analogy to the green paradox. It's not a so-called strong green paradox. Okay, so I think I'm going to quit on that point here. I'll leave the conclusion slide up and see if anybody's got any questions in less than 25 minutes. See?
Great.